Hello everyone, welcome to SwitiSpeaksOfficial YouTube channel. This is System Verilog Essential series, where we are learning complicated System Verilog concepts in very easy language along with a lot of coding examples. In the previous lectures in this series, we had learned about interface and modport. Today we are going to see a detailed example which will have your interface and modport. I'll explain you each and every line of the code very properly. This design will seem complicated, but don't worry, I'm going to explain it to you very properly in easy language so that you can understand this thoroughly, the design as well as Testbench. Let's get started. First, let us understand the design. This is the design of a memory. So if you see here, I have a module mem which represents memory. And here I am instantiating an interface. So let's see an interface also. Interface is nothing but a connecting bridge between design and Testbench. You will have the instance of the interface in design as well as Testbench. Let me first make you understand what is this interface. Here, if you see, I have an interface which is named as MEMIF. MEMIF stands for memory interface. It has one input signal which is clock. And then it has these ports. Let's understand these ports. The first port is the reset signal. Then there are some ports for system and there are some ports for memory. I'll explain you these ports. This port is command valid system, which says whether the command is valid for the system. This is ready sys, which says whether the system is ready to accept your data. Then we have write enable for the system. We have data for the system, that is 32-bit data. The address which we are having is of 8-bit addresses. And then we have the ports for the memory. So for the memory, we have the input data, which is 32-bit. We have output data, which is 32-bit. And we have the 8-bit address. Then we have the write enable for memory and chip enable for memory. These are the different ports inside your interface. Now, we had gone through the concept of modport. If you have not already gone through, please go through. There is a complete video lecture on modport along with examples. Please go and understand that example. There you will know what is a modport and why do we use it. I'll just give you a gist. Modport is used to assign the directions to your interface ports. If you see in the definition, we are defining all the ports as logic. We did not give any direction, whether it is input, output, in, out. We didn't mention. But we want to specify the direction depending on our requirement. And for different modules, the directions can be different. And how many ever flavors of the directions you need for the ports, that many modports we have. Here we have 3 different modports. One is for system, one is for memory, one is for Testbench. Let's understand this. This first modport is for the system. It's named as sysmod. Here you have some inputs: clock, reset, the write enable for system, which will tell whether the write enable is there, then you can perform the write. Then whether the command for the system is valid, that is also input. Address to which you want to write data in system, that is input. And data out mem sys input. All these are inputs. Then the out signals are write enable for memory, chip enable for memory, address of the memory where you want to write the data, input data for the memory, and whether the system is ready to accept the data. All these are outputs. And we also have ref, which is data sys. If you remember, I have told you in modport, the port type can be input, output, or even ref. So this is one ref type. The next modport which we have is for memory. Let's understand this. Here you have some input ports and output ports. Input ports are clock, reset, write enable for memory, chip enable for memory, address for memory, and data, input data for the memory. And we have one output, which is output data for the memory. Then we have the mod port for the test bench. Here you have clock, you have ready for the system. In the outputs, you have reset, you have write enable for the system, you have command valid for the system, and you have address for the system. And you have one ref, which is data for the system. This is the interface definition. These many ports and 3 mod ports. One is for system, one is for memory, one is for test bench. Now, next we will understand the design. In the design, I have a memory. Here, if you see, I have 256 locations. Each location is of 32-bit wide. Now, this memory can perform 2 different operations. One is write and one is read. Here, if you see, write and read all will occur at the passage of clock. First, understand, to the memory, we are passing an interface instance. Here, if you see, memif is nothing but your interface, and this mem mod is the mod port which we have for the memory. You can see this mem mod is the mod port for the memory. It will decide the directions of the ports. So these are the directions of the ports. You will have input as clock, reset, write enable of mem, chip enable of memory, address of memory, input data of memory. These will be your inputs, and you will have one output, which is output data of memory. So these directions will be decided here because you are passing the mod port. And I am naming that instance mem mod I. This memory is having 256 locations. Each location is of 32 bits because we have a 32-bit data. So like this, you can have 256 datas of 32-bit. This is your memory size. Next, the memory can perform 2 operations. One is write and one is read. Write and read both will happen at the passage of clock. Here we are passing the clock, and this is the mod port instance. If you remember, this is the mod port instance which helps in deciding the direction. For us, the clock is input, right? So this is at the passage of your input clock. If you have the chip enable of memory, because memory chip needs to be enabled to perform any operation, be it write or read, the memory chip needs to be enabled first. And if write enable is present, first chip enable should be there and the write enable should be there. And why we are using this mod port? Because it helps in deciding the direction, and we want to decide the direction. Both write enable and chip enable are inputs. So when these 2 inputs, which is chip enable and your write enable, are 1, only then your write operation will happen. What we will do? In the address, whatever address you have in that particular location of your memory. See, I am passing mem and your interface dot address of mem. So whatever address you have in that particular location, inside your memory array, only in that particular location, this particular data will be written. This is your write operation. Write the input data to the memory in the address of the memory. Read operation, what it will do? It will read the data from the memory. When should read operation happen? First thing is your chip enable should be high. Chip should be enabled. And second thing is your write enable should be 0. Because if write enable is 1, then the operation is write. But if write enable is 0, then the operation is read. So chip enable is high and write enable is low. Then your whatever data is stored inside your memory location, whatever address you have, From that location, your data will be read and it will come as the output to your data out. If you see mem mod, this particular port, it has one output which is data out mem. So this particular is the output signal. We are reading from the location mentioned inside the address and putting that data into the output data signal. This is your read operation. Simple. Now the memory will have some states, like it will be idle, it will be in write state, it will be in read state, it will be in done state. It means the operation is done. To control the memory, we always have a memory controller. So we will understand the design of the memory controller now. Here I have a module named memory controller. And here also I am passing a mod port. Which mod port? Now this is for the system. Memory controller is the system. So here if you see, the mod port which I am passing is sysmod. Here this is the particular mod, sysmod. Here we have certain inputs, we have certain outputs, and we have a ref. Now here understand, first if the state is idle, the first state for the chip will be idle. When after reset, when the reset is done, the first state will be idle. In your idle state, all your ports will be 0. Your system is not ready to accept the data yet. Your write enable is not there. Your chip enable is not there. You don't have any address or data. Everything is 0 in the idle state. And your data to the sys is Z. Okay, so these are the reset values of your ports. Now, next is, say you are in idle state. In your idle state, your system is not ready to accept data. Now, when you get the valid command and write enable for the system, here if you see, command is valid and write enable is there. In this scenario, what will happen? We will get some value of the address and some value of data, because your command is valid and you have the write enable. So whatever value of the address or data is there in the system, the same will be there for the memory. To the same address we will write. This address and data will come from your memory controller. And then we will also make write enable to the memory as 1 and chip enable to 1, because we want to perform the write operation. Write operation can only happen when your chip enable is 1 and your write enable is 1. Hence, to perform the write operation, we do this. Now you have the write enable, you have your chip enable, you have your address, you have your data. So you can perform write operation. That is why we will change the state to write. Next, when your command is valid but your write enable is 0, it means the operation which is to be performed is read. During read operation, again we will copy the address sys value to the memory address. We will copy the data sys value to the data in, and write enable is 0 because it is a read operation. Chip enable is 1. Of course, chip should be enabled, but your write enable should be 0. This is the major difference between your write and read. If you see, your write enable will be 1 because you are performing write operation. Here the write enable will be 0 because you are performing read operation. And then we will change the state to read. It means from idle, you can either move to state write or you can either move to state read, depending on the value. First, your command valid should be there. And second, if your write enable is 0 or 1, depending on that, it will be either write or read operation. Now, when you are in write state, what will happen? When you are in write state, that time, if your system is ready for sending the data, ready for receiving the data. This is your system ready. Then when your system is ready, that time what you will do? You will give your system is ready. We are making it as 1. If it is in right state. Why? Because your system needs to be ready in right state. Now, say your command valid went low. If your command valid went low, then the read and write operations can't proceed and your system has to move back to the idle state. Initially, when you are in write mode, we will make the system ready as 1. But as soon as you get that command valid is 0, that time we will reset everything. Here, if you see the address, input data to memory, write enable, chip enable, everything is getting reset and we are moving to the idle state. Now say you are in the read state. When you are in read state, again we will make the system ready as 1. We will give the output memory data to the system data. We will get some data from the memory because we are reading. When we are reading, memory will give you some data which you can get inside your system data. This will be as soon as you enter the read state. We will make ready sys ready signal as 1 and whatever output data of the memory we will assign to the system data. Next, when you are in read state and command valid of the system is low, again we need to reset everything. So here if you see address memory, data input memory, memory input data, write enable and chip enable are 0. System is ready for the data because currently you are in read state, and after this is done, after your read is done from the memory, then you will move to the idle state and even you will make the data of the sys as set. These are the different states inside your memory. Understand all this properly, how these state transitions happen. If you want, you can go through this. You can go back, scroll back and understand this. I have explained each and every state properly. You can go through until you understand. You can revisit this video again and again because you need to understand these states. Now we have understood interface, we have understood the design of memory, we have understood the design of memory controller. Now let us understand the test bench, because test bench will drive your design. In the test bench, I have a program. I had already covered this program block in very detail. If you go through System Verilog Essential series, which is uploaded on SwitiSpeaksOfficial YouTube channel, the previous video lectures in this series, you will see a detailed video on program block. If you have not already gone through that, please go through. It will help you understand about the program. Now I will make you understand this code. So we have a program block which is meant for the test bench. Here a program block is enclosed inside the keywords program and end program. Now understand how we are giving the inputs. Here I am passing a interface mod port mem interface dot tb mod. Tb mod is meant for the test bench. You have certain inputs, you have outputs and you have a ref. This is the instance of the TB mod port. Now here what I am doing, I am initializing some signals. I am making reset as 1, write enable for sys as 0, command valid as 0 initially, address also as 0 and data of sys as z. Initially I am just resetting all the values, you can say. So at this time the chip would be in which state? Idle state. Later on, I am making the reset to 0. We are making the reset to 0. After that, we are having a for loop because we want to test writing to 4 different memory locations, and we will read from that. Our aim is we will see if the data which we have written is coming back. That will confirm whether our design and test bench are working properly. Whatever data I am writing to the address, that same data I should be able to read. Now, what we are doing, write and read operation happens at the pause edge of clock, correct? So at the pause edge of clock, I am making system address to whatever value of I. So it will loop through. First it will write to 0 location, 1, 2, 3, like that. It will write to 4 different locations. I am randomizing the data. It will generate a random data. $random is for randomizing. Even I have created a very detailed series itself on randomization. If you see SwitiSpeaksOfficial YouTube channel, you will see a complete series on randomization where we have discussed different ways in which you can achieve randomization in systemverilog. You can go through that. There we have also discussed about $random. $random will generate a random value for your data. Your data is 32-bit, so it will generate a 32-bit random data. Then command should be valid. In order to perform any operation, read or write, your command should be valid. So we are giving command valid as 1. Now before reading, the data should be written. That's why initially we are making write enable to 1. There should be some address, there should be some data, the command should be valid, and the write enable should be there. These are the conditions to perform the write operation. You can check here. You can check these are the conditions to perform your write operation, which we are following, right? Next thing is, when your system is ready, only then the write will happen. So whenever your system is ready, that time we will write the data to a particular address, and we are printing. We are printing the time at which the data is written, we are printing the data, and we are printing the address. Then after some time, we will wait for the pause edge of clock. We will make the address 0. We will make the system data as Z. We will make the command valid as 0. Your write has completed. And we will make write enable as 0. This is completion of your write operation. We had written to 4 different memory locations. Now let's wait for 11 clock cycles. Then again we will loop through and we will read whatever we have written. So we are looping through 4 times because we have written the data 4 times. And this time what we will do, again the address, we will read from all the address. So we are looping through the address. It will take the value 0, 1, 2, 3 depending on the loop. And then your command should be valid to perform the read operation, and your write enable should be 0. Once all these conditions are there, we will wait for the system to be ready, and once the system is ready, at the pause edge of clock, you will read the data from the memory, and we are printing it, whatever data, whatever address, and the time. After you read, we are making the system address 0 and command valid as 0. So finally, inside this program block, we are passing a stimulus to write some data into the memory, and then we are reading the data from the memory, and we will check whether the data which is returned to the memory is matching the data which is read from the memory. Now we have the test bench. In the test bench, I am giving the name as memtb. I have to generate a clock. So first, initially your clock will be 0, and after 10, you are seeing a delay of 10. I am making clock plus plus. It is a 1-bit signal. So it's your wish. You can make clock plus plus, or I can make not of clock. That a clock plus plus is also fine. So it's your wish how you want to generate the clock. So it's a 1-bit signal. So 0, 1, 0, 1, 0, 1, like this it will loop through. This is the clock generator. I am generating the clock. Next, what I will do? I have to create the instances of my interface, my DUT, everything. So here I am creating an instance of the interface. Now in the DUT, I have memory and memory controller. So I am creating instance of memory controller. I am creating instance of memory, and I am creating instance of my program. And to everything, I am passing the same interface. Same interface. Once all this instantiation is done, all these inputs will flow through your design. It's the same interface, right? All these inputs will flow through your design. The data will be returned to the memory, and when you read, you will get the data from the memory. This is how it works. Now let me show you the output. Our main aim is we have to see whatever data we have written to the memory. Are we able to read the same data? If that is correct, it means our design and test bench are working properly. Now here I have written to 4 address. You see these are the data which is written, and these are the data which are read. If you see, all the data are matching. At address 0, whatever data I have written, I am able to read. Same at address 1, 2, 3. It means my test bench and my design are working properly. This is how you can use interface with your memories. Like this, you can practice for various different designs. I hope this example was very well explained. Each and every line of the code I have explained. If you still have confusion, please go through this video again. I'm sure after going through at least few times, you will understand it thoroughly. And another thing is, try to code this example by yourself. Understand it first, then code everything by yourself. The memory controller, this interface, your program block, your test bench, code everything by yourself and run it. This will give you a very good confidence that you have already created a small memory design and verified it, right? So go through this, practice by yourself, and I'll see you in the upcoming lectures. You can stay tuned by subscribing to SwitiSpeaksOfficial YouTube channel. Thank you.